Hi, my name is Daniel Yang. I'd like to share with you about our work on composer classification. Our problem statement is to classify unseen piano sheet music, audio, or MIDI by composer based on its compositional style. In this work, we consider a 9-way classification task among well-known classical composers. This talk has 4 parts. First, I'll give a brief overview of previous work in composer style classification. Then I will introduce the 3 main contributions of our paper. The first contribution is to propose several musically informed data augmentation strategies. The second contribution is to demonstrate cross-modal transfer learning, in which a model trained only on sheet music images is used to classify audio and MIDI queries. The third contribution is to demonstrate the effectiveness of our trained models in a one-shot learning context. Let's start with a brief overview of previous work in composer style classification. At ISMIR 2020, we proposed a way to perform composer classification of sheet music images using language model pre-training. During training, we convert sheet music into a bootleg score, which encodes the locations of note heads relative to staff lines. The bootleg score is a 62 by n binary matrix, where 62 indicates the total number of staff line positions in both the left and right hands. We then convert the bootleg score into a sequence of musical words by encoding each column of the bootleg score as a 64-bit integer. Once we have converted the sheet music into a sequence of words, we can then train a language model on unlabeled data to predict either the next word or randomly masked words in a sequence. Finally, we can use the pre-trained language model weights to initialize a classifier and fine-tune the classifier on the composer classification task using a small set of labeled data. At test time, we convert the sheet music into a sequence of words, as before, and then classify the sentence using the fine-tuned classifier. This approach was proposed last year and is representative of the state-of-the-art in composer style classification. Now we will introduce the first of our 3 contributions, which is to propose several musically informed data augmentation strategies. The key idea is to generate musically plausible variations of existing data. One obvious strategy is to consider key changes, which correspond to shifting the bootleg score up or down, while being careful not to shift notes across the boundary between the left and right hand staves. We also consider several augmentation strategies based on the insight that randomly removing notes will still yield a musically plausible event. We explored 3 variations of this: dropping individual note heads with some probability p, dropping the left or right hand with some probability p, or dropping an entire bootleg score column with some probability p. Note that these 3 types of data augmentation can be considered a musically motivated form of dropout applied directly to the raw data. This figure shows the performance of several models without data augmentation on the sheet music composer classification task. These are the results presented at last year's ISMIR conference. The 4 groups at the bottom correspond to 4 different model architectures: a CNN model, AWD-LSTM, Roberta, and GPT-2. For the architectures that are based on language models, the red bar shows performance with no pre-training, the yellow bar shows performance with pre-training only on the labeled dataset, and the green bar shows performance with pre-training on all piano sheet music images in IMSOP. We can see that pre-training substantially improves the performance of all models. Now let's look at the effect of the proposed data augmentation strategies. This figure shows the improvements of models when we use the musically informed data augmentation strategies. The red-colored bar at the right shows the performance of the GPT-2 model with data augmentation only. We can see that the data augmentation has an even bigger effect than pre-training on all IMSOP piano scores. Furthermore, using both pre-training and data augmentation results in huge performance improvements. For example, when adding data augmentation to the IMSOP pre-trained GPT-2 model, performance increases from 0.67 F1 to 0.95 F1. The second of our three contributions is to demonstrate the effectiveness of cross-modal transfer learning. Here, we train a composer-style classification model entirely on sheet music images, as before, but then apply the model to classify audio or MIDI queries. Audio queries are first pre-processed with the Onsets and Frames automatic music transcription system, and MIDI data can then be converted into a bootleg score using the conventions of piano sheet music. The audio and MIDI queries were taken from the Maestro dataset using the same 9 classical composers. The queries are fixed duration fragments randomly sampled from the data, and the queries are evenly balanced by composer. This figure shows the results of a cross-modal transfer learning experiments. The 4 groups at the bottom correspond to the same 4 model architectures as before. Within each group, the different colored bars correspond to queries of different duration, ranging from 10 seconds to 60 seconds. The colored bars indicate performance on MIDI queries, and the black horizontal lines indicate performance on audio queries. We can see from these results that transfer learning is highly effective across modalities. For example, the GPT-2 model achieves a 76% classification accuracy compared to an 11% accuracy for random guessing. The third of our 3 contributions is to demonstrate the effectiveness of our trained models in a one-shot learning context. The question we wanted to answer was, how well can we classify unseen composers? To answer this question, we measure how well we can classify fragments of music from 9 unseen composers when we are only given one example piece from each composer. These queries were again taken from the Maestro dataset, but using 9 composers that were not seen in the labeled dataset. Our approach is to use the penultimate layer activations of the trained classification models as a feature representation, and then classify test queries using the k nearest neighbors distance. These are the results of our one-shot learning experiments. This table shows the classification accuracy of the 4 model architectures on classified short, fixed-length bootleg score fragments from MIDI or audio data. We can see that all models perform much better than random guessing. This indicates that the trained models are capturing a generalizable notion of compositional style that extends beyond the 9 composers in the labeled dataset. In closing, we'd like to summarize our 3 main contributions and their potential impact on the ISMIR community. Our first contribution is proposing several musically informed data augmentation strategies. On our composer classification task, this data augmentation has an even greater impact than pre-training on all piano music scores in IMSOP. This suggests that these forms of data augmentation and others like it should always be used on tasks involving symbolic representations, since their effect may trump other factors like pre-training and model architecture. The second contribution is demonstrating the feasibility of cross-modal transfer learning. This suggests that for tasks where there is little training data in the target modality, it is still possible to use transfer learning with models trained on a data of a different modality. For example, any tasks involving classical piano music can use a model that is pre-trained on all IMSOP piano sheet music. The third contribution is to demonstrate that our model's representation of compositional style generalizes to unseen composers. This representation of style could therefore be useful for many other tasks beyond our specific 9-way classification task. This may include other tasks like music recommendation, genre classification, and many others that are of interest to the MIR community. Thank you very much for your time and attention, and I'm happy to take any questions that you have.